Stars are whispering tales of old, planets spinning, stories bold. Life is dancing through the night, countless worlds in the starlight. Galaxies full of mystery, infinite in their history. Beyond our dreams and our sights, life blooms in the cosmic lights, dancing on the edge of space. Take me away, feeling the universal grace. In the dark our hearts ignite, life across the endless night. Nebulas with colors bright, birth new wonders in the light. Comets trail their sparkling tears, life endures through the years. In the silence of the void, every heartbeat is enjoyed. From the depths and to the heights, life expands through cosmic night. Dancing on the edge of space, and off we go, feeling the universal grace. In the dark our hearts ignite, life across the endless night. Dancing on the edge of space, and off we go, feeling the universal grace. In the dark our hearts ignite, life across the endless night.
Hey everybody, welcome to SkyTour live stream. It is I, Mark D'Antonio. I'm here with you tonight. Daryl has a night off, and we're going to have some fun tonight anyway. There's a lot of cool things to look at in the sky, and we will be doing so. Right now, we actually have the telescope trained on Uranus, the brilliantly teal colored planet at the far reaches of our solar system. It's about 19 astronomical units away from us. That's or from the sun. It's 19 times 93 million miles. That's a long distance, and it's got a bunch of moons of its own. And this is Uranus right here. Obviously, there it is. And you might not recognize the color, but if we actually move it, you'll see its color. So I'm gonna get out of this for a moment. All right, and I'm going to move it. You see that color here as we moved it? That's before the sensor gets saturated with the color. So we're in a 10-second shot, so I wanted to show you the comparison. So there's a quick shot. Then when it gets saturated, it looks like that. We'll just go back here just real quick to a 1-second shot, and I'll drag it. Now when I drag it, you'll see the color. And you can see the color there actually. Okay. And we can zoom in a little bit. All right. And as I drag it, let's drag it to the east. We'll drag a telescope to the east. You can see that brilliant teal color. Well, you could anyway, but there it is. It kind of went too fast. But that brilliant teal color is actually the color that is Uranus. And so Uranus is actually a very cool planet. You know, its atmosphere is composed mostly of hydrogen gas. It's it's a smaller Jovian world, a gas giant. Saturn is bigger, and Jupiter, of course, is the biggest. But you have Uranus. Now, Uranus is interesting because its orbit is cocked at an 89-degree angle. That means that where all the other planets are like this, if you look at me down in the lower left, all the other planets are kind of like this. Earth's on a tilt. But the planets are roughly vertical like this. But Uranus is like this. So it's rolling through the solar system as it orbits. Isn't that cool? And so why is it doing that? You know, all we can think is that maybe there was an ancient collision of Uranus way in the beginning with some primordial mass of some kind, and that primordial mass was enough to tip it on its orbit to that particular angle. So when we look at it and we look at the moons, which we'll go in now and check out the moons again. So I'll make this we'll make it a 12-second shot. All right, and we'll get out of the low light mode and go into our deep sky mode. Okay, you can see the color. The color of Uranus looks really good there. That's actually a good rendering of the color. Okay, so that's the previous shot. I'm going to clear it, and we'll get the new one coming in. Okay, here it is. And now you can see, when we look at this is sort of a close-up right now. These are stars out here. But you notice we've got these 1, 2, 3 objects. There's a fourth one here that will show up shortly. This thing in the middle is a star. This here and this here are moons of Uranus. Now, how do I know? Let's go look. We'll go into our planetarium program. And here's Uranus here. And you'll notice we have Oberon, which corresponds to this first dot. We have a star in between. Actually, we have Titania next, okay? And this is the star. Okay, so we have Oberon, Titania, and then this star right here. So Oberon, Titania. Let me just move this a little bit. Oops, wrong way. Let's do this. Okay, center it back up. All right. So we have Oberon right here. We have Titania right here, and a star right here. So these are two of the moons of Uranus right here. So it's interesting how Uranus being so far away, we can still see the moons going around it, which is kind of cool. You know. And now, how big is this actually on our screen? Well, on our actual view here, it's this big. Now, you'll notice this kind of glow here. That's because we still have the light of sunset interfering. It's light that you can't even see with your eye yet. I mean, it's if we go here and back out, okay, we come way back out now, and we go to the western horizon. You can see that it kind of looks like it's dark over there, but we still have the light of the day fading a little bit faster, and so it'll be gone in a little while, and this glow will be gone, and it'll all end up being a dark sky. All right, so that's neat. Now tonight we're going to look at a few other cool things too that are up in the sky. I just want to welcome everybody that's here, by the way. I saw a few people that I know and think the world of. Okay, first of all, we have Tiffany is with us, Tiffany Echo. Tiffany is, of course, the other half of Michael Tarr, the better half, I suppose. And I just got brownie points. And she and Michael are responsible for the equipment giveaways that we do on our channel, on our shows. So we owe them a great debt of gratitude. Yes, I was going to say a great grit of datitude. That's good. Anyway, Kurt's with us. Hi, Kurt. Kurt W75. What's going on? Nice to see you. Keith Evans is with us. Okay, Stan from Two Rivers Observatory. Sam S. Genghis is with us. Rockstar is with us. Judy M. Hello. And Michael Galea, who said something and then got rid of it. I guess I don't know. But anyway, it's okay. We have Everdeen, 58. Nice to see you, man. And Daisy and Zoe Amethyst, of course. You know, Daisy and Zoe have been here like for years with us. Years. It's incredible. Nito. And right now we have Karen Belmont too. Carl Becker, Donald Kunzer, Ron Regier. Ron Regier is cool. He's in Rimrock, Arizona. I know Ron, good friend. You know. And by the way, if you ever want to know anything about petroglyphs, okay, the guy in the chat right there, Ronald Regier, that guy is probably one of the coolest guys on the planet. Can tell you almost everything about petroglyphs. If you remember petroglyphs, those are those, you know, pecked in stone. I did a lecture once called Drawn in Stone, and he helped me greatly in interpreting some of the petroglyphs, and I owe him that debt of gratitude as well. But he's the guy to talk to if you ever have any questions about that. And of course we have Native NC. How you doing? And Jorge Cortez, how are you? Nice to see you. Hey, and we have Macho Man. What's up from Flagstaff? How you doing, man? Good to see you. All right, so again, this is Uranus right here, and we'll zoom in now again. Now we've got 20 shots taken of it, and we can start to see a little more detail. This is Oberon right here. This is Titania, and this is a star, kind of in a line, which is kind of cool. Okay, so that is interesting when we look at this, because we are looking at something that is basically, oh gosh, I think it's the distance is huge. It's actually almost 19 and a half astronomical units from the sun. So that's 19 and a half times 93 million miles away from us right now as we look at it, and we can see some of the details. Now, this telescope is a wide field telescope. The field that we're looking at here is literally 3 full moons across by 2 full moons tall. And because of the quality of the camera, we can zoom way in and still see some things. But the next telescope we'd love to put into Benson, we have the telescope already, courtesy of some nice donations that we got from people in SkyTour. And the telescope, if we can put it in, it's going to go on a mountain with other professional astronomers. I'm a professional astronomer. That's what I went to school for. And so I'll be right at home up there. And the guys in the buildings next to us are all going to be doing research. And we're going to be doing public outreach. That will be the only outreach observatory in the entire mountain, which I think is kind of cool. You know, and the nice thing about that telescope, no, Ron, that's fine. The nice thing about that telescope is that we're going to be able to look at planets like Uranus, Jupiter, Mars. We're going to be able to see details on the face of Jupiter and Mars with no problem. Uranus maybe not so much, because Uranus is rather featureless. Okay, but we're going to be able to see lots of details. Now, we could use help. I mean, go to skytourlive.org. If you feel like you could donate to us, help us out, please do, or join our Patreon and help us out that way, because we're trying to get our Benson Observatory Fund up and running so we can do this. Our target is the middle of February to do the installation. That's next month. So if you can help us out, that'd be wonderful. So anyway, enough of the begging. Now let's go on and do some astronomy, shall we? So let me darken our background up a little here. You gotta pull this curve. This is the dark level here. See, if I bring it up too far, we'll lose some of the details, okay? So if I go past the curve, you'll watch what it does. Jamie, there, you at least see you lose some stuff. If we go right to the top, that's the best darkness level, but we get grain, and the grain has to go. And the only way it goes is with quantity of frames. But again, we have Uranus, a cold world out there. Pretty neat. Yeah, so that's neat. So, And so we have Kevin who joined us here. 45 degrees. Yeah, it was actually in the 40s here in Connecticut where I am. The telescope up there that you see above me, that's 2,600 miles away in the Arizona desert, the Sonoran Desert, west of Phoenix. And it's out in the middle of the desert where the sky is stunning. How stunning? Well, we can go to our all-sky camera, and it's still not quite dark enough yet. There we go. Okay. So let's go to our homepage version of this. So you can see, there we go. So here's Venus over here, setting right here. Okay. Then we have Jupiter. Okay. We have Aldebaran right here. We have the Pleiades. And of course we can click this. This is going to be made available to you anytime. And I'm trying to work on getting this published to the web so that you can do everything I'm doing right here. We can also show you time lapses of the previous night, so we can come in here and go down and look at the night of the 16th, which was last night. This is the day, sunrise, sun is coming up, and you can speed it along, okay, and check out in the evening when you get to the evening. Now, last night it was cloudy. We were going to stream, but as you can see, this is why we couldn't. We had clouds boiling through. It's actually kind of rare. We have over 300 clear nights a year in the desert, you know. So we couldn't do it last night. That's the moon illuminating this, by the way. Okay. So in any case, we have some really cool stuff that we do with this system. We have another one of these all-sky cams, which I made for this observatory. It was a project that I did, and I'm using Thomas Jaquin's all-sky camera software. It's on GitHub. And here's the summer Milky Way setting and the winter Milky Way coming up. This glow in the east here, this is the lights of Phoenix, almost 80 miles away. How about that? So a sensitive camera can pick those lights up. All right. So we have lots of stuff to look at in the sky. Yeah, we're going to be doing some of that tonight. Now, we minimize that. Come back to our Uranus picture. Let's show you where Uranus is in the sky. Let me back out. Okay. And I'm going to make this a little bigger now, just like I did before. Okay. All right, so as we back out, you'll notice that Uranus is kind of high in the sky, because right down here, this is the horizon down here, the southeastern horizon. And it's above the southeastern horizon by a substantial amount. Look where the telescope's pointing, right? It's pointing way up in the sky. You know, it's actually not all that far from a Triangulum galaxy, which we'll view next. Pretty cool. Now we also have the Pleiades over here, and we're gonna look at those as well, so you can see the amount of dust that's around the Pleiades stars. But we're going to go to the Triangulum galaxy first. So you got a good view here. This is Uranus, and what I'm going to do, I have an identifier system, but it doesn't recognize planets. Sure, lie to me. Look at that. It just did. How about that? Okay, so Uranus is here, so we're going to actually make that the target name. All right. And it didn't recognize the other night, didn't recognize one of the planets. I thought, oh, it doesn't know them. Okay, so that's our target name, and it's up here in our target box. And then what I'll do is I'm going to save this, and I'll save it just like you see it here. So if you want to, you can go download it and check it out for yourself. That's it. We're going to go back to our 1 second low light mode here. So each of the exposures here is a 1 second low light exposure. All right, so we can actually see the motion as we move things, but it's going to be kind of dragged out. So what we're going to do now is we're going to head up to the area just a little bit north of us here. This is the constellation of Triangulum up here, and it's really just an incredible location because it's got this beautiful galaxy in it that we can actually see the Orion Nebula things and the nebulae that are in this Triangulum galaxy. And the Triangulum galaxy is 2.7 million light years away. 2.7 million light years away. That's pretty far. That's just pretty far. Now, what we're trying to do here is just center the galaxy. And because we still have some bright sky here, I'm going to actually increase our gain a little bit to help us with some detail. Okay, so now let's do this and see where the galaxy is. Here it is. It's right here. See that fuzzy? That fuzzy is what you might see in a smaller telescope. Okay, but we're going to bring that up into the view. Actually, what I can do is do something even cooler. I'll identify it. Okay. There we go. And I'll say, take the Triangulum Galaxy right here and center it. Center it into view. And it will do it. I could move it into place, but now this is an annotation system that we're using with our software, which is called SharpCap. It was written by Robin Glover. He's a very, very smart guy. And, you know, I've talked to Robin a number of times. He's very approachable. And he makes the software for us to be able to capture and see everything that we're doing. And he's able to add a lot of features to it, which are really nice. I've asked him for certain features, and he's done them, which I think is cool. By the way, if you want one of your own SkyTour travel mugs that has a nebulae and things on it, you can feel free to go to our Etsy store, which is bing. Where is it? It should be right up there. Let me see if I can make it show up. It's not showing up. It figures. Yeah, it's not showing up. Okay. Well, anyway, the Etsy store is another thing that is available to you to actually go and grab some of these really cool things that we make. We put them on products of all kinds: cups, mugs, clothing, luggage. You can get a giant Orion Nebula on a luggage that you take with you. You'll never miss that luggage at the airport. Carry bags, gym bags, things like that are all cool. So, that said, that's pretty cool. So now, let's do this. There we go. Alright, so the Etsy store right there, and I store that up in the corner here where you can get at it. It's not a link, unfortunately. But the Etsy store is SkyTour Shop. You can go check it out, get something you like. And what we'll do now is I'm going to start an exposure to show you what's hiding in this dimness over here. Now, here we go. We're going to go and we're in low light mode right now, but I'm going to do a 25-second shot. Now, you have to understand, our telescope is literally been made 25 times faster than it was natively. We added a lens system to it called Hyperstar, courtesy of the folks at Star Arizona in Tucson, Arizona, and Dean and David and Steve down there. These guys have been crazily helping us to get our observatories going. And as a result, you know, this is the kind of thing you get to see. That red is the holdover of the sunset light, by the way. But we will, I'm gonna color correct that just like this. And I'm going to correct these a little bit. Okay, let's go to this. Alright. This is our full width half maximum filter. If the stars get bloated, they'll go above the dotted line. And so we'll keep them below the dotted line. That way we'll have round stars and never have any problems. Alright, so now let's, these are our color curves, by the way. We have red, green, and blue. And this white one is the average of the three. This yellow one is the actual data that's being taken. So if we move this is the black level. If we move this black level out, it gets brighter because we're including more of this other data. But usually the main data is up by the top of the curve and over the top. So what we do is we approach the top of the curve, but we don't go past it. So we go just before the top of the curve, and that makes it the darkest it can get. Look at that. Okay. Now we can see detail in this galaxy 2.7 million light years away. And one way we use to try and get rid of some of the early noise that we get in the image, because we only have 4 frames stacked, I'll explain that in a minute, is we drag the mid-level down a little bit, and that softens the noise. Now look at that. That's just gorgeous. And so we can even right now zoom in on this a little bit. Wow, you're seeing this galaxy as it was 2.7 million years ago. Think about what was going on the Earth back 2.7 million years ago. That was when the light you're seeing just at this instant left this galaxy. Isn't that incredible? Traveling between galaxies for that long, just to be intercepted by your eyes on your screens tonight. And that's it. Then it's gone forever. Quite a mission light has. Okay. So, if you look in here, you're going to notice some interesting things. You'll notice that there's some different colored areas. We've got these greenish areas. We've got these areas here. In fact, I'll do it this way so we can remember. You got these greenish areas over here. Okay. We got these reddish areas here. We got one here. And there's actually a lot more. We also have these little tiny dots in here. Little tiny things. What are those? You know, we've got many of these. Okay. Here's another greenish area right here. So we got all kinds of stuff in here. And you say, well, wow, what is that? You know? Well, what that is, all right, is these greenish areas, these are supernova remnants, where supernovae occurred. These areas here are areas where stars formed, are still forming, and that's why they're blue, hot, young blue stars. These areas here are stellar nurseries, massive stellar nurseries. Okay, this is a giant stellar nursery here. Here's another giant stellar nursery here, another supernova over here. And these little dots I told you about, globular clusters, like Messier 13, like Omega Centauri in our galaxy. Clusters, like they look like snowballs of stars. Okay? And they're just beautiful. And so we're seeing them from that kind of distance. It's really amazing. And these things, because it's so far away, any changes to the galaxy take a long time for us to see because it's so big, you know. However, it's not nearly as big as the Andromeda Galaxy, and the Andromeda Galaxy is nearby, actually, relative to this. And if you want to see that, maybe I'll show it to you. You gotta let me know. Okay. And so this beautiful, unbelievably beautiful object is a very blue galaxy. It has these blue spiral arms of hot young stars. The stars in the middle are kind of yellow and older. That we call those population 2 stars. These are population 1s, which mean the younger, hot blue stars. These are the things. These hot blue stars are what end up making supernovae. Eventually. Here's another supernova remnant right here. See, and you've seen supernova remnants with us if you've been here with us. You've seen the Veil Nebula. And you've seen the Spaghetti Nebula. I know, strange names. And you've seen some other nebulae that are supernova remnants, and they're very cool. And that's because of hot young stars that live out their existence and run out of hydrogen and any other element they can fuse. And when they run out of everything, they collapse. And when they collapse, they explode, and that makes a supernova. Because gravity wins the fight. Because as they're fusing stuff, they're pushing out with massive amounts of radiation, and that holds the star up. It fights the gravity trying to crush it. So that balance it reaches is an equilibrium called hydrostatic equilibrium. And when they reach this hydrostatic equilibrium, they sit in that state for the stars, the massive stars, for a few million years. For stars like the Sun, they'll sit in that state where we are now with hydrostatic equilibrium for billions of years. And so billions of years are really, really a long time. Let's see here. Louis Rodriguez says, Mark, could you point in a comment C/2024 G3 Atlas? I would love to, except that it's below the horizon already. It's very, very low to the horizon. It's not up, and we cannot see it at this point. And that's no matter where you are in the United States, for instance, you won't be able to see it. It's best viewed in the southern hemisphere. So it's peeking above the horizon briefly, but we won't be able to see it. So that all said, I think it's really cool. Now, DPFX, how you doing? Good to see you. C&D boy, we know him. And Catherine Messick, how are you? You know, you guys are great. It's so nice to see you. Randall Smith, hey man, I forgot to say hi to you. Sorry. Yeah, and so here we go. We've got 16 shots stacked. Now, what does that mean? Okay, we take the first shot and it's kind of noisy. Remember that noise we had, like modeling with colors and stuff that didn't belong there? But what we do is we take a second shot, align it with the first, and stack it on top. And then we just make this image sandwich until we have a whole stack of these color images like this. And the fact is, the noise that you see is random on each shot. So it randomizes out the noise. So now when we zoom in, it looks way better than if we would have zoomed in earlier. Okay, so we can see more detail in here. You can see details in these beautiful dark rifts of dust that we see in the galaxy. By the way, these dark dust rifts come from those supernovae I told you about, and from old red supergiant stars that are so big and distended that they make molecules of dust in their outer atmosphere and get sloughed off sometimes. And then end up floating out into space. And so you do that trillions of times, and you end up with dust clouds throughout the galaxy. We have them. This galaxy has them. Andromeda has them. Most galaxies have dust clouds like this. There are some that don't, and those are called elliptical galaxies, and those are weird. Yeah, as C&D Boy says, Canada Boy. Don't forget to subscribe and click on the likes. And yeah, thank you guys. That would be fantastic. You know, and we are working on an app. We have it in testing. It's for Android and Apple iPhone and computer, Mac, and so forth. And it's the SkyTour Livestream Observer's Companion, and it allows you to look through years of our photos that we've taken and download all the ones you want. And by the way, whenever we save images like this, like I'll save this one right now. Okay, we have 20 right here, 21. So I'm saving it right now, and it's saving it to a directory called Triangulum Galaxy, blah, blah, blah. Okay, and then I'll save exactly as seen, and this saves a ping file. And this ping file, which you'll see right now, this is what you get when you actually download this. This is yours to take. And where do you get it? Well, it's actually, as we're speaking, it's being uploaded to our cloud server, and it's going to be right here at skytourlive.org. You go to skytourlive.org right there, okay? And skytourlive.org, scroll down, you'll see all kinds of stuff we offer up there. And you'll see, take me to cool pictures. I want to get cool pictures. And you read the instructions there, and you go there. So that's sort of like the kludgy way of doing it now until our app is available. Once the app is out, you can just click on it and download it directly to phones, to computers, anywhere. It works really great. And it was written by Izabela Melamed, our Bulgarian super user of SkyTour Livestream and super fan. We owe her a tremendous debt of gratitude. So this galaxy has these arms. You'll notice they're not very clean. They're kind of all over the place. And so this galaxy is a galaxy that's known as an SC, spiral for S, and then C, meaning spiral arms are kind of like disheveled and loosely wound. Now, when you look at spiral arms in a galaxy, you can see them right here. Here's a spiral arm right here. Look at here. Okay, going there, right? And if we could actually, I could just kind of draw this arm in. You can see the arm here. Okay, you see another one right here. See another one right here. Okay, and here, and here. Okay, here. See how that's going? So you actually see these arms going out, okay? And what these arms are is areas where new stars are being formed. But they would, you might say, well, how come over time they don't wind up and just become like, very, very tightly wound? And the answer is because, and they do, in other words, when you look at our solar system, Mercury goes around the sun in 88 days. Pluto takes well over 200 years to go around the sun. It's farthest out, right? Farther out, I should say. And so the farther away from the center of something, the slower they have to move, right? Well, that would mean that the spiral arms should have wound up a long time ago, with the center spiraling up and the outside slowly spiraling up. But that's not what we see. We see that the arms are sometimes loose like this. Now, how can that be for a galaxy that's been here for billions of years? And other galaxies its age don't have arms that are that loose. They're much more tight. Some are even looser still. So how does that happen? Well, the answer comes down to looking at the new concept of dark matter. Now, there's something called the Tully-Fisher relation, which actually measures rotational speeds of stars and galaxies. And when you look at the rotational speeds of stars and galaxies, you'll find that the stars in the outside spin much faster around, or revolve much faster around the galaxy's nucleus than they should have. In other words, Pluto would be found to be going much faster around our sun, almost as fast as Mercury, which makes no sense. Okay? So why is it that we find galaxies are spinning like almost rigid disks? So like my hand spinning like this, okay? But not quite, because as my hand spins, the arms get a little bit distended out and they drag back a little bit as they spin and drag out. But how come it's spinning like a rigid disk? And that's because we've theorized, and we have evidence now, of dark matter, which is a matter that we can't readily detect. And it's not dark energy. Dark energy might actually be a myth right now. We might have gone down the wrong path when we talk about dark energy, but that's another thing. So dark matter is matter that's called non-baryonic matter. Okay, non-atomic, like the atoms we're used to seeing, like hydrogen and helium and carbon and so forth. Okay, but it adds mass. It's like a halo around every galaxy, so that as the galaxy rotates, that dark matter has its own mass, which is helping to drag those arms around. And although we do have differential rotation, meaning stuff in the center does go around a little bit faster than stuff on the outside, so the arms do kind of drag out. As you can see, we drew that picture. You can see the arms are dragged out a little bit. Every galaxy has arms that are kind of dragged out a little. Well, that's because of this subtle differential rotation from the nucleus on out to the farther extremities of the galaxy. And so when it rotates, it's actually rotating outside of the understanding of normal physics without the use of dark matter. And that's what has been the hang-up for astronomers and cosmologists and astrophysicists, is that the galaxy rotation has always been a conundrum that we cannot figure out until we discovered the potential that dark matter is involved. So dark matter is why galaxies spin almost like regular, just solid disks. And again, like I said, it's not quite. The outer extremities do drag back a little. They move a little bit slower on the outside. But this is pretty, isn't it? Let's see if we can do some processing. I'm going to back out just a little bit. Center it up. Okay. And let's bring this guy in here, and let's bring in some detail. Okay, and now let's do this. Let's go to the center right there. Oh, look at that. Yeah, that's pretty. That's a beautiful galaxy, guys. Beautiful galaxy. I'll go a little bit too much on that. I'll back it out a little. Wow. That's pretty. Okay, we have 36 shots here, so we'll save it. again here. And this is going up to the server, as I mentioned. You can find it at skytourlive.org. And when you go up there, you can take down this exact photo as you see it here. Now, if you join our Patreon, which you see across the top of the screen there, then starting at $10 a month, you can actually get 4 highly processed, finished, ready to zoom into images a month that we provide. And for higher tiers, it starts at $10. For higher tiers, you can actually get access to all of the images that we have. And that's cool. Okay. So, like I said, this is free for you now. You can take these guys, and that's all most people want, But if you're a free Patreon member, that's great. But you might want to consider helping us out, because we do have a second telescope we're going to move into Benson, and we're calling it the Benson campaign. And we're trying to get this telescope in there. We visited the building. We've got an agreement, and we just need to get the money for the pier. The pier is costing us $1,500. I know, astronomy's not cheap. I'm not expecting someone to come up with that money for us. But what I'm saying is, we have to get the pier, and then we'll be paying a monthly fee to be on the mountain with the other astronomers. We're going to get the internet and electricity for the fee, and that's $400 a month. So that's about half the cost of everywhere else. So Benson, Arizona is actually darker than where we are now by a tiny little bit. It's darker by a little bit. And we're going to be able to view things that we haven't seen because it's farther south by about 200 miles. So that's going to change our coordinates just a little. Anyway, there's 40. We're going to change it right there. We're going to say save. And save as scene. And there we go. And there is Measure 33, the Triangulum Galaxy for you guys. All right, nice. Let's go back to our low light mode here and move on to the next item up for bids on The Price is Right. Okay, so we're going to zoom out now. There's our full field, as I told you. It's 3 full moons across by 2 full moons tall. Okay. And let's see what our night sky looks like now. Yeah, it's looking pretty. Yeah. Now, you wonder where we're looking. We're actually looking over here. This is Andromeda. So we're looking over in Andromeda here. With and Triangulum right here. So that's where we were looking. I don't know if you can see the galaxy here. I wonder if you can. Oh yeah. Okay, yeah. There's the Andromeda galaxy right there. It's a little tiny bit there. Triangulum galaxy is too small to see here. All right. So that's our all sky. All right, and that's in the startup song you saw a bird butt sitting on this. We don't have any problem with birds anymore because we have a anti-bird spinner going all the time out there now. It's going right now. Okay, let's let's do this. DVFX says Andromeda strain. Ron, if your screen is blurry, make sure you're in 1080p. Okay, because we're broadcasting it in HD, so you should be able to see it without it being blurry. Okay, if anyone has that problem, Ron said his screen is blurry. Make sure you're in 1080p. Tim F, what's going on? Nice to see you. Michael Glaze says 41 in Reno. Wow. I know you said that a while ago, Michael. Okay. All right, so Karen Belmont, always complimentary. Thank you. Ranjit, how are you? Yeah, actually, you can see the H2 regions. What he's talking about, NGC 604, remember that bright nebula in the Triangulum galaxy that I showed you? That's what that was NGC 604. That was a hydrogen emission region. We call it H2, Roman numeral 2, because it's ionized hydrogen region, which results in a reddish glow. And so we saw that. Yeah, Richard McFarland, hi. Nice to see you as well. All right, let's go now up to our planetarium view. And we are over here in the Triangulum region. And we're going to go check out the Andromeda Galaxy now. The Andromeda Galaxy is actually a little bit closer to us. It's 2.4 million light years away. Not 2.7 million. But you'll notice how close these two are in the sky. Now, there's a reason for that, and that is because they're actually perhaps interacting with each other. Okay. Alright, so let's see here. I have to get my bearings here. Oh, I went to a star. My mistake. Wondered why I couldn't see it. Okay. Alright, and this will be better. There it is. I had the wrong object selected. I'm a dummy sometimes, guys. Well, this is the heart of the Andromeda Galaxy. You'll notice there's a fuzzy object here. We'll talk about that as well. But first, what I'm going to do is I am going to bring the telescope south a little bit, because the galaxy goes all the way up out of the picture here. It's huge. It's several degrees across, much bigger than our field. But what I'm going to do is I'm going to go to about here. This is going to go out of view for now, but there's going to see another one coming in right here. Those are satellite galaxies going around the Andromeda Galaxy. And then I'm going to head to the west of the telescope, bringing this nucleus, this bright nucleus, way over here. And you're going to say, what are you doing that for? You'll see in just a minute, because there's so much more data here that you don't even know is there. You know? So we'll do a couple of shots showing you this here, and then we'll do the other showing you the other side. It's just incredibly large. And there is truth. There is truth that we are actually going to be colliding with the Andromeda Galaxy in a few billion years. That is true. It's heading right for us. Yep. And the thing is, it won't change a darn thing here in our galaxy. It won't affect us in the slightest. Okay. So right now, this goes all the way down here and even continues off the screen. There's a lot going on in here that you don't see. Every one of these stars you see here, those are in our galaxy. Okay, and so we're going to be looking way out here at something 2.4 million light years beyond. Okay, so let's do another 25-second shot here. Okay, and while we're waiting, we're going to go into we're going to get out of our low light mode and go into our deep sky mode. And you'll see the Triangulum Galaxy from in the last buffer. That's what's in our buffer. And you can keep looking at that. That's not harmful. Because as soon as we get this data to come in, it's going to overwrite that. Okay. Yeah, look at that. A lot of Andromeda there, isn't there? Now, this is the first shot. You notice how it's kind of got that reddish hue. Okay, we're still waiting for the last vestiges of sunset to go away. All right, so we'll get rid of it with a color correction, and then I'm going to change our curves and make it a little more subtle. All right, and right away with the Andromeda Galaxy, you can see some beautiful ribbons of dark dust. That is something else. That dark dust is something that's never far from a galaxy. Okay, except in the case of an elliptical galaxy like this one here, or the one that's just out of shot up above, I think. It's just out of shot. It's up here. We'll get there in a minute. But I want you to see this area down here. And what I'll do is I'm going to start bringing it out. I think our full width half maximum has just got to climb a little bit more. Yeah, we'll do that. It's our roundness quotient for the stars. I got to bring it up a little bit higher. Because, you know, no guiding is perfect. If we look right here, you can see this is called a drift graph. You can see of the exposures we took that, you know, some of them are varying back and forth by a fraction of pixels. You know, and then we have this one here showing you that we had some guiding errors too. However, we can guide around that, you know, and so we're doing that now. Okay, so let's now do this. Let's try to bring up some contrast. It might be a little noisy, but this will help us see what's really going on there. We're looking at a beautiful galaxy 2.4 million light years away, the Andromeda Galaxy. And what do you notice right away? What do you see when you look here? You see this, right? You see this, okay? You see that little reddish area right there? Yeah. This is an area where there's a lot of hot young stars, and the hottest and bluest stars in the universe are type O. That's the letter O. Okay, and you have O 1 through 9. Then the next level is B stars, B 1 through 9, B 0 through 9, I should say. Sorry, and O 0 through 9. And so when you look at these stars in these locations, they tend to be all O and B stars. So they're called OB associations. And so we see OB associations here and here. And there's also lots of hot young stars, O and B stars in here as well. But these are extremely pronounced areas where there's lots and lots and lots of these. And so we see those, and they can actually become more obvious as I do this. Okay, let me make that even more obvious. I go to the top of the curve. Okay, so now you see how bright they are. Okay, and then I'll color correct again, because every so often you want to color correct. Yeah, so now you see these blue stars here. This is a beautiful area. However, I can tell you this: if you were there, you probably wouldn't survive it. It's very hot there, a lot of ultraviolet radiation, because these O and these B stars give off lots of ultraviolet radiation. You know, it's the stuff that tans you, but in the type of strength and intensity you get from this guy, this location, it's the stuff that'll kill you. So we want to be really careful about that. Okay, so Ron Regier asked a question earlier. Sorry I missed it, Ron. You said, Mark, is that dust, real dust like on my TV, or much larger? Actually much smaller, Ron. These dust grains that you're seeing here are about a micron in size. Now, a micron's what, 10 to the minus 8 meter? I mean, we're talking about an extremely small piece of dust, okay? And so that kind of size means that you're looking at a very, very small, tiny little spindle of dust. But it's also, it is a molecule. To be visible, it's going to be a molecule, even at 10 to the minus 8 meters. So we're looking at that, and what happens is this dust is very good at reflecting back to your eye blue light. In fact, it takes in the red, orange, yellow, green, blue, indigo, and violet, the rainbow of colors that every star has, even red stars. It just has more red than blue, but you still see some blue. And when you see that spectrum, the these particles are very good at scattering the blue light coming into them from the starlight. We see that effect here on Earth in the molecules of our atmosphere. They scatter the blue light from the sun. So during the day, our sky is blue. And you're looking at the blue component of the sun's light everywhere you look, because everywhere we look, the molecules are absorbing and just re-emitting the light in all directions. So everywhere you look, we see blue sky. So that's why you have a blue sky. The actual process, for those that want to look it up, is called Rayleigh scattering, Rayleigh, Rayleigh scattering. And there's several kinds of scattering. You have Compton scattering too, and that's what clouds do. They reflect everything. That's why they're white. And clouds are accurately reflecting the light of the sun. The sun is actually white, almost white. People say, "Oh, the yellow sun." Well, it only looks yellow because some of the blue light's been taken from it by the molecules. Out in space, it's actually white, nearly white. So, all right, so we've got 15 exposures here of the Andromeda Galaxy right there, the lower portion. And you can see these vast star clouds down here, these curling spiral arms of dust. Okay, and dust tends to be in the spiral arms because that's where the hot young stars, like in these OB associations, are born. And so when they die, they usually go supernova. And when they go supernova, all that dust is pushed back out into the interstellar medium to be utilized to make planets at some other location, at some other time, and some other history point. Really cool. All right. So we have 17 here. We're going to save it here. Let me, first of all, identify it, make sure that it knows what we're looking at. Yeah, it does. That's me, sorry. Okay, so we're going to take the Andromeda Galaxy right here. We'll make that the target name. I could just type it in if I want to, but we're going to do that and get out of it, and now we'll save it. And now we're saving it. Now, again, SkyTourLive.org. Go there, and as you scroll down, you'll see after the donate now, you scroll down, and you will see there's a section about getting to cool imagery, and there is where you will see how to get to these images. Again, until our app is ready. All right, so I'll save it one last time. Actually, I did that already. I'm going to just save exactly a scene one last time. Okay. And Ronald Regier says, "Thank you, Mark. So much to learn. So much fun to learn new things at my age." Okay, I'm glad you found your 1080p, your 1080 setting. That makes it able to be able to see everything on the screen, Ron. Otherwise, what fun is it, right? Okay, so we got that. We're going to go back down to our low light mode here and find our way to here. Okay, right there. And now what we'll do is we're going to move this down. Okay, and now you'll see this other galaxy come in up here. This is the satellite galaxy coming in here in a minute. There it is. Okay, you can kind of see the disk. The Andromeda Galaxy is something you can actually see with your eye, which many of you know. Okay, so now we're going to go take the telescope to the east to bring in this corner, bring in this northeast corner of the galaxy. You notice how you can see it while it's moving, but when it stops, it suddenly seems to vanish. That's an effect of the eyes. The eyes are very good at recognizing motion of dim things. Evolutionary holdover to when we're looking for predators stalking us in the woods. I'm not going to go too far because I want you to see this. That's going to be good enough. That'll show us. Okay. So now we'll see. I'm going to actually bring us down a little bit. Just enough so that we can catch this diagonal. This will be the biggest amount. All right, that's good. Okay, so again, 25 seconds. And by the way, I want to thank you guys for joining me tonight. This is really cool. All right, and we'll go back into our live stack. You'll see the previous stack we did, which has been saved. There it is. That's the southwestern side of the Andromeda Galaxy. Yep. Hey, Brian Bruce, how are you? Yeah, Brian, I mentioned earlier that 2023 G3 Atlas is actually very, very low to the horizon, and it sets very soon after sunset, so we cannot see it. But we do look at comets all the time. Actually, we look at supernovae that are happening actively in galaxies. We've done that too, but this is not available to us, unfortunately. It's best seen in the southern hemisphere, actually. Okay, so here is the upper part of the galaxy, and now what we do is we actually put those two together for the people in our Patreon, and we give them a beautiful mosaic of several images. Okay, we're gonna just take the color correction, apply it. All right, color correction helps us, and then I'll just do this. I'm gonna take this black level and move it off the curve a little to kind of brighten the background just a little. All right, and that helps us with early data detection. So you'll notice up here, okay, the reason I wanted to show you this, in the galaxy down below in the lower right down here, we saw those OB associations, those hot blue stars. Well, guess what? Up here we have more. Look at that. We also have a very bright red nebula here. There is more red nebulae and like Orion Nebula type nebulae in here as well. You can see them kind of all over the place. And when we get more imagery, we only have four of them right now, 4 stacked images. But as we get more, you'll see quite a bit more here of this. I'm going to move this up just a little. Okay, take it back a little. Let me take it back some more so we can actually check it out. All right, let's color correct also. Get rid of any of that sunset light as we can. There we go. That's more accurate. Now you can see these star clouds up here with these hot blue stars. Okay, really, really thick up there. Now that's the place you want to live, is right in here. You know, actually we're kind of in that now in our galaxy. Now here is an elliptical galaxy. This is a satellite galaxy like this other one. That one down there was called Messier 32, the one that was right about here. And this is Messier 31. Charles Messier found these, and this is Messier 110. And one thing to notice is I mentioned that, you know, galaxies usually all have dust in them. Well, this galaxy is an elliptical, and they usually don't have any dust. This has a distinct line of dust in it. So this is a rather interesting phenomenon in this galaxy going on, that we see a dust lane inside here. Doesn't make any sense. Okay. Now, I won't go all the way to the high number of images we took, because I want to take a look at something else. Okay, so there's the Andromeda Galaxy that we are looking at. It's actually on the other side of the pole right now. I've got this skewed a little bit. Okay, so that's more like it. And what we're going to do is, after we're done with this, we're going to come down to this guy and check it out. Because I mentioned supernovae, and you saw supernovae in the galaxy of the Triangulum Galaxy, but what you didn't see is a supernovae like in our galaxy. And we've seen them before: the Veil Nebula, okay, the Jellyfish Nebula, and so forth. The Bubble Nebula is a Wolf-Rayet star, but then we had the Spaghetti Nebula. And so, okay, so 10 will do it here. We'll say save. Okay, we're still Messier 31, which is good. Okay, save exactly as seen. Okay. Thanks, Doug. And so now, okay, this is the thing. So you see this dark dust in here. Let me just, I'm gonna do this. This is an over processor. This will actually process it much higher than it should be, but it'll show you what's hiding in the background. Okay, so you can see that it goes right off the view. It goes right out of the view. There's so much more in this galaxy out there. See? And that's pretty cool. And let's see if we can color correct that. What does color correct do? It lines up our red, green, and blue curves together. Okay. Now, when you over process like this, you kind of get a false color view. It takes subtle reds that don't belong there and it really amplifies them, which is kind of no good. So, but that's all right. All right. So we have 12. We'll save it. Be done. Victor Anthony, hey, nice to see you, man. Thanks for coming in. All right, so let's get out of the Andromeda Galaxy now and go back to our low light mode. And then we'll head to Supernova Remnant, which is going to really startle you if you haven't seen it. It's got the most incredible filaments and tendrils in it. It's really amazing. So here's our full field again. And we're going to do a focus run too when we get there. All right, so here's the Crab Nebula. We're going to check it out. We also have this, which it's just an H2 region. I don't want to do that right now. All right, here we go. Let's just go here to the Crab Nebula. You watch the telescope over my head swing over. There it goes. It's swinging around. All right, and the crab should be coming in just momentarily here. It'll be a little fuzzy ball, a little fuzzy spot at first. There it is. Now, it's quite a feat to keep a telescope aligned on the night sky, especially from 2,600 miles away. So you get the telescope aligned as best you can, then you have tools on the fly to help keep it aligned, and that's what I'm doing tonight. I'm using like this right here. This is the finder that Robin includes in his software, and you see there you have M1 Crab Nebula. Now we're going to center it into view, okay, and say yes. All right. Okay. So now it's going to move down into the center of the view. So this is the exact center. So now that I know that the crab is there in the center of the view, what I can do is come back over here and zoom in on this and make sure that the telescope is exactly aligned with it. And there we go. Now it's synchronized, and it changes all the coordinates everywhere to make sure it's all connected. All right, let's check this out. This is really cool. We're at now, you know what? I should give you a little bit of a reminder, a refresher of what we're looking at here. Okay, first of all, this section is our telescope control section. Okay, this is our telescope computer. These two views are our telescope cameras inside the building. This view is of, well, go away. Okay, and this view is our main view. This is our camera control cluster. All right, this exposure line right here and the gain are the two most important fields for the camera. Gain is sensitivity of the sensor. Okay, right now it's set to 200. It can go up to about 600. But the higher you make that gain, the more noise you get, and the many more shots you have to take to get rid of the noise. But since I'm doing outreach with you guys, I don't want to make you wait 30 minutes to see the Crab Nebula. I want you to see it in 20 seconds. And that's what happens. This is our overprocessor. This is our focusing. This is a secondary telescope control. So there's a lot going on in here. And all of it means something to us. And Karen Belmont says, the blur in the center. Yes, that blur in the center is the object we're about to take a picture of. But first, I'm going to use the focus segment, as I told you before, and I'm going to refocus the telescope. Now you see as you focus, the stars get out of focus. They look like that. When you go out of focus, what's cool is the telescope colors of the stars become much more prominent, which is kind of cool. All right, so we're going to let this build a focus curve. It's going to make a parabolic curve. The bottom of the curve, the lowest point, will be where the telescope star images are the smallest, and that will be a perfect focus. Sheldon Harrison's with us. How you doing? Nice to see you. Way too cloudy at Sheldon's place? Well, it ain't cloudy here. Check it out, Sheldon. Here is our night sky. Now, that's 2,700 miles, 2,600 miles from me, but I live vicariously through my telescope. And I welcome you to do it with me. JSCO 77, one of our past prize winners, is with us. Hey there, GSCO. Okay, we're going to let this curve build. You're going to watch it make a curve. And at the logical bottom of the curve, it's going to calculate the lowest position, and that will become our star's focal position. And then when we take the picture, it's going to be really, really cool. Ronald Gear just says, I just ate a slice of homemade eggnog bread. Go away, man. Come on. Eggnog bread. I've never had it, but I'll love it. You know, I'm going to make it to Rimrock. I'm going to visit with you and Dar. I am going to have a good time. And we'll check out the other buildings, the other domes in Rimrock to find out who runs them. Where Ronald Gear is, there's a guy that has 2 telescope big domes on his property. There we go. Look at that. So here is our curve, and there is our best focus position. I'm letting it finish out. It's at step 10 of 12, and it'll calculate. You'll notice this little number is going to change a little bit, and that'll be the precision focus location. See, it just changed, so now it's going to focus. And when they line up, boom, we're done. So now we have perfect focus on the telescope. So I get out of that. Okay. And I'm going to click on my temperature coefficient here. Let's see how the coefficient works tonight. All right. And now we're going to do, I'll explain that in a minute. So now we're going to do a 25-second shot. Now I can do 10-minute shots, okay? But I don't want to make you wait for all that. Here's 25 seconds on a faint supernova remnant in the constellation of Taurus. It was actually seen in 1054 AD by Chinese astronomers. How could they see it? They didn't even have telescopes. That is correct. But what they had were their eyes, and this was such a bright supernova, you could see it during the daytime and see it as a new star in the night sky, all right, even during the day. Now, the thing about that is that supernovae are, as I said, bright. Look at that. And this brightness is something that you're going to catch and see with all these supernovae. All right. So this supernova was so bright that they documented it and said, wow, that's something that we've never seen before. And it became known as this 1054 AD object. That's, the year. And so when they saw it, they documented it. It became a real fixture. And in the 1700s, when Charles Messier did his catalog, it became Messier number 1, the very first one. All right. You'll notice it has these filaments in it. There was a star here, and it blew itself to pieces. It blew up at the end of its evolutionary life cycle. We'll talk about evolution of stars another time, but it is amazing what happened here. Hey, Roni. So let's zoom in a little bit here. You can see the colors already forming. All right, and I'm going to move this black level right near that peak again to darken everything up, because there's something I want you to see, and it's here inside. I don't know if you can see it. You can see it right now, but I'm going to draw a box around it. You see inside that box? You see that little white dot right there? That white dot right there? You know what that is? That is the remains of the former star. It's called a pulsar. Now, what's a pulsar? A pulsar, see, stars can have several different end states. A star like the sun will shrink down to become a white dwarf when it runs out of hydrogen and all that. Okay? It'll be a white dwarf. And that white dwarf will be about the size of the Earth. Okay? A star that's bigger, okay, and that goes supernova is going to be very massive. Our sun can't go supernova, not nearly massive enough by a long shot. So it's going to swell into a red giant and then slowly shrink down to a rather quiet death and become a white dwarf, leaving a planetary nebula around our area in space where it sloughed off its outer layers of the star. Okay. However, in this case here, this star was much more massive than our sun, and it went supernova. And so the next end state of a star is that of something called a neutron star. Now, I can talk about the reasons why a white dwarf is cohesive. Okay, that's called electron degeneracy pressure. I can talk about why neutron stars are held up by neutron degeneracy pressure, whatever. That bottom line is there's mostly neutrons in this star. And the making of neutrons in a star happens when you have massive stars like this. And I can show you how it works someday, but not tonight because I don't want you to fall asleep. So, bottom line is, okay, we got time. Bottom line is, this tiny dot that I pointed to a little while ago, right there, that tiny dot, that's the pulsar. Now, and this is thousands of light years away, by the way, thousands of light years. Now, it's expanding. In over 100 years, we've actually made a movie of it going like this, expanding outward. Okay, eventually, it'll get far enough out so that the glow will stop, but the material will still be in the interstellar medium for use to make new planets, new stars. Okay, and we'll talk about the colors in a second. But that little white dot is a pulsar. It's exceedingly bright, and it's so bright for its size that you can see it thousands of light years away. How big is it? It's the size of Manhattan Island. Okay? Manhattan Island. That's a massive, that is a tremendous size difference. Okay? Yet we can still see it from this massive distance away that we are, because it's so bright. Yeah. So that's how these work, and they're bright blue, by the way. If we can zoom in, we've got 11 shots taken right now. If we can zoom in, you might be able to actually see that its color is different. Yeah, you can see that. It's blue, it's a little blue. I can see that we're out of focus still a little bit. I think the temperature compensation failed. Didn't do what it was supposed to do. So I will redo that and get us back to proper focus here. All right. Sorry, I'm a bit anal when it comes to this. I want to make sure that the focus is correct. So I'm going to do it. Okay. Okay. Alright, so now let's do this. And do this focus again. I have to resample the focuser and get the right coordinates, because I have not lately. I just thought it would work. I gave it a try, it didn't work, so we'll start again. Anyway, I want to just mention to everybody that I will be in Arizona starting February 4th through the 11th, and going to try to install this new telescope. So any help you can give us would be great. Go to skytourlive.org, click the donate now button if you want. Join our Patreon, help us out, because we're doing free astronomy. There's nobody doing what we're doing. Absolutely no one doing what we're doing. There are people that are doing astronomy online, live, but there's no professional astronomers that are coming out and doing literally classes for everybody just off the cuff like this. Nobody's doing that, you know, and I'm happy to be doing it. I think it's pretty cool, you know. There's nothing stopping me because I have a passion about astronomy, and some of you know this. I decided to become an astronomer at age 9, and I didn't change. I've never ever wavered on that, you know. crazy. You know, some people say you should get a life. Yeah, I know. I guess so. I'm wondering if my curve is gonna find a 0 point. It may not. Hey Carl, thank you, man. That's so kind. Yeah, it didn't find our focus, so I will get it. Okay. Yes, I know I'm moving the focus. Okay, it's about there, but I'm going to redo this. All right, let's see where we are here. All right, here we go. All right, now let's go positive. Oh, I think I know what happened. I went the wrong way. Ay. Okay, my bad. All right, so now we can do it. It should work now. Oh yeah. Hey, thank you guys for your support of us. This is great. Does anybody remember when we started? I think we started in 2016, didn't we? Wow. Hey, Rockstar. I think we started in 2016. Oof. Doing our focus run, then we'll do the crab here. And by the way, every moment we take to do this means that Orion is coming up higher and higher in our sky. And I'll show you what that means for us, because when we look here, right, we have 37 cluster, we have this, and we have the Rosette Nebula here, we have the Orion Nebula. Like right now, the Orion Nebula might be a little low for us. Its altitude is, oh, look at that, 44. We might be able to shoot that too. Hey, all right. Let's go here and see what we got. There's our center point. Okay, so we got our focus. And I can kind of, it's at 9. I can say best focus because that's not going to change that much. It'll move to best focus. Brian Bruce says, you do have great lectures. Everyone should come and watch you at Ozark Mountain Company. Oh, you were there. That's cool, man. Yeah. Yeah, I'm not. I you know how there's speakers, they go up to the podium and they stand behind the podium and they kind of hide behind the podium and they read their notes. I don't fault them. They're there and they're standing out there, putting themselves out there. I love it. But I just can't stand behind a podium because there's too much activity going on, you know, and I want to be out in the audience. So most times I'll actually go out in the audience and I'll do my lecture from the audience. You know, the thing is, I don't need notes. I know my stuff. I know what I'm talking about. You can tell I'm not reading any notes now. So when I do a lecture, I actually just have bullet points. And the bullet points, I could spend an hour on each bullet point. But I don't. You know, I obviously have to be cognizant of the fact that people need to sleep sometime. Yeah. Okay, so this will be the previous shot. This was a little out of focus. All right, this should be good now. Brian, were you there at Ozark when I did the history of the Earth talk? Oh, you did. He said he did the toilet paper. Yeah, I actually used toilet paper to show people the history of the Earth. I took a roll of toilet paper and I put the entire history from the time the Earth formed to the time that we were in that room right then and there. And I did it on a roll of toilet paper. And I I literally walked out in the audience. I walked around the center section of the Ozark conference with it. Yeah. I think that was really cool. It was a good talk. I still do that talk. In fact, that's one of my most requested talks. Say, can you bring your toilet paper? Why don't you have any in your bathroom? You know. It lends itself to jokes like, you say, I brought something along to help us all, and I've used it so many times before. And I pull out a roll of toilet paper, and they go, I used it before. Not this. This is clean. This is brand new. Okay, so now we're getting a clearer shot here. Let me zoom in and make sure we got a good, clear shot. Yeah, okay. See, now you can see that pulsar right in the middle there. It's really obvious. And you'll notice that its color is kind of blue compared to the surrounding stars. Now this red right here, this red is hydrogen neon emission. Okay. This green and is sort of like a teal. This is actually oxygen, doubly ionized oxygen. And you'll say, well, how do you know all that? Well, you know that by the nature of how these atoms actually ionize. And once you figure that out, once you know that, then you're able to figure out exactly what colors they generate, because the universe is all color, right? It's the obvious transitions in atoms that make these colors. And why do we know what color it's going to be? Because when you look at the atoms frequencies, the frequency of the transition, there's a certain wavelength that they give off in light, and that wavelength is the thing that tells us the color, because the wavelength is the color. So it's pretty cool. So if we see that something's giving off light in the 350 nanometer range, we know it's exceedingly blue. If it's doing it in the 6500 or 650 nanometer range, we know it's red. Okay, so hydrogen's up there. Okay, 6500, 656 nanometers. The oxygen here, that's in the greenish teal, kind of going toward the blue. Okay, so it's around 4,000 or so, 400 nanometers roughly, plus or minus. And so we know based on the frequency what colors we should expect in these atomic transitions, because it's all about the transitions. Okay, so let's see. Ron Regier says, "Yep, I held the beginning of the Earth at the Phoenix meeting." Yes, that's correct. You did. I did the Phoenix Mutual UFO Network meeting, and Ron, of course, was there, and he was the star of the show because he was the beginning of the Earth's history. It was kind of cool. Yep. Second only to the formation of oxygen in our atmosphere. That was another big high point. Kevin says, how do you get to the Patreon? I sent a sum, but I couldn't find the monthly part. I'm not phone friendly. Thank you, Kevin. That's good. If you go to the SkyTour Live, you on the upper right corner, there's a link to take you to the Patreon, and you can subscribe to one of our tiers. I think we have $3 a month, $10, $25, etc. I would love it if you can help us out. That'd be great, man. That's cool. Look at the filaments. These are beautiful. If you need further help with that, what you can do, Kevin, is when you go to skytourlive.org, you can click to contact us, and that'll come to the emails for me, Marianne, or Tara, who we're the three that put this all together. We don't make any money in this. We're not making money. We don't take a dime. We're putting it all into equipment and to try and make sure that we bring the best experience. So, okay, so this here, we've got 12 shots. This is nice. We can live with that. We'll say save here. That's measure 1. The very first object that Charles Messier decided to put in his catalog. Sure thing, Kevin. Like I said, email us and we'll be happy to help you figure this out. Yeah, so over 100 years we've watched this, and we've watched it getting bigger and bigger and bigger, and we can't, it's again, because it's hundreds of light years across. Okay, we cannot find ourselves, I forget the exact diameter actually, but we've discovered that when we look at this, it's expanding because the initial explosion pushed material out, and that's really interesting. And so we've been watching that for 100 years, and there's a video of it expanding. You can look it up. Crab Nebula expansion video. Look that up, and you'll get it. Don't do it now, though. Wait for us, you know? So, I think it's really cool. Alright, let me just do one thing here to... Yeah, okay. 6,500 light years away is how far away this is. And you can see something the size of Manhattan Island in the middle of it. Look at that. That's how bright that is. Isn't that incredible? That's massively bright. Bonnie is with us. Hi, Bonnie. How are you? Yeah. Blue light doesn't go through the walls, Bonnie. I know what you're saying, though. You might be seeing reflections of the blue light under the door, maybe on the edges of the door jambs, subtle reflections that your eyes are having trouble seeing. Because your eyes are not as sensitive to blue light, so that's kind of why it hurts your eyes a little bit. But it allows you to see, to like walk around, for instance. That's why on warships they use blue light in the command and control areas, because that blue light is the least sleep-inducing light. Our eyes aren't that sensitive to it, so their screens and everything literally jump out at them, and it makes you actually more focused. So, but the blue light you don't really see that well. Green is the light you see the best. Okay, we're gonna go to 20 on this and then save it and move on. Okay, the distance across is actually 11 light years, so I was mistaken on that. I don't know why I said the other. However, it is definitely 6,500 light years away. It is beautiful, JSEO. It really is. Okay, we're gonna save it now. Save exactly a scene. Do one more thing. I'm going to bring up the target and reorient it. There we go. Now I'll save it with the annotation so you actually get this information in the file as well. Okay, I like doing that. Well, there's the crab. It's funny because the first time I saw the crab, I was a little kid with a small telescope, and it didn't look like this. I can tell you, I didn't see all these filaments. I didn't see these filaments until we put this particular camera on this particular telescope. And I gotta say, the first time I saw it, I think I squealed like a pig. I was like, "Wow!" I couldn't believe it. I was seeing it. It was so pretty. Okay, let's go to our 1 second shot, because this will accurately show you what I saw in my telescope. Not that. Okay, but that fuzzy thing, that's what I saw, and that's all I saw. I couldn't see anything else, you know. So it's pretty faint. All right, so now what we can do is we can rock it on down to here and check out. Oh, we got so many things to look at here. Well, we're gonna jump right down here to the Horsehead Nebula. Okay, and we're gonna do that. So, and we're gonna see if we're gonna be able to see it. I think we can, but we're gonna look. You watch the telescope; it's gonna be bending over quite a bit, and what we don't want is for the telescope to interfere. Well, I don't think it is because that's on the talk. So, and there's Sigma Orionis. Yeah, we got it. Cool. Full view. Nice. Okay, this star looks fuzzy not because there's clouds, but because we're actually looking at a reflection nebula. One of those nebulae I told you about where the dust particles scatter the blue light from the star and cause it to only show as a blue cloud. And it's the dust. So the horse head is right here, but you can't really see it. So what I'm going to do is I'm going to move us over to the east a little bit. Okay. If you haven't seen this before, okay, you're in for a real treat. This is stunning. And by the way, just so you know, this is the first time I've imaged it with this camera. This camera is specifically tuned to this particular telescope, and I've not used this here before, so I'm expecting greatness. What can I say? It's gonna be pretty. Okay, so let's move a little more to the east because there's another star right here that I want to bring into the view. Yeah. Okay, so we have two stars that have blue reflection nebulae around them. The horse head is right here, and Sigma Orionis is illuminating. Its ultraviolet radiation, as a matter of fact, is causing this hydrogen gas in this local region in Orion to glow. All right, it's ionized the hydrogen gas, and when the electrons go back into the atom, because ionization is when the electrons get bounced off the atom, when it comes back in, it gives up the energy it used to get off the atom, and it does that in the form of light. And the light is the red light we were talking about before, hydrogen alpha, 656 nanometers. Okay, so now we're gonna do a exposure that's gonna make you rethink what's up there in the night sky. Okay, so here we go. We're guiding, so I'm gonna do this as a 25-second shot. You guys are in for a treat. Okay, I'm gonna go to our deep sky mode. Get ready, guys. Hello, Heinz Sherry, how are you? That's our previous shot of the Crab Nebula that we looked at. And now you're gonna see the Horsehead Nebula and the entire environment around Sigma Orionis. Look at that. Look at that. Wow. Here, we're going to do something else too. I'm going to take this down and I'm going to move this over, give us a full view, and we're going to actually look at this full screen. Look at this. Now, this is the Horsehead Nebula, and this here, all this is dark dust in here, and it's out here too. Orion is one of the most dusty regions that's close to us, and the dust in the Orion region is so dense, relatively speaking, and I'll explain what that means in a minute, that it's actually molecules. All right, and the molecules are molecules of carbon and silicon and other elements that were discarded when stars blew up. Okay, and this is beautiful. I'm going to go into our histogram here. That's my this guy here. I'm going to pull this up just a little bit closer to show you the real nature. Okay, and we're going to color correct. Okay, look at that. Wow. And now we'll pull this down just a little. All right. So this beautiful wall here is at the edge of a giant molecular cloud. In fact, the molecular cloud stretches throughout Orion almost and beyond, and that's called the OMCC, the Orion Molecular Cloud Complex. In there you find clouds of molecular dust, of all kinds. These molecules can be big and small, micron-sized stuff, or a little bit bigger. And in a sugar cube size area of space, the density can be as high as 30 atoms per cubic centimeter for sugar cube. Okay, kind of a cubic centimeter sort of. Okay, and 30 atoms is not a lot compared to our atmosphere, which has like 10 to the 19th atoms in a sugar cube size space. So you'll say, well, then why are you saying it's dense? Well, because it is. It's actually dense for a dark cloud. You got to remember, these clouds are light years across. And when they start to collapse on themselves, okay, there's areas where the clouds have begun to collapse. Okay, we're seeing up here, okay, I got to get my full width filter here. Yeah, we lost, so I got to go a little higher. All right, so now we'll start getting them in. So when we actually did this, when we actually look at the color here, this molecular cloud, the density can vary. Now, in areas where the cloud, the material in the cloud begins to congeal and condense within itself, that of course becomes much denser, and that can become dense enough to create planets. And the hydrogen gas, which is this red part, okay, is mixed in with the dust. The hydrogen can form new stars, and that's what happens in this region. We see new stars forming all the time. Okay, we also know that in the Orion region, we found that there are also planets that have formed that have no star associated with them. They're called rogue planets, and we see that that's happened here too. Right, so let's zoom in on this just to kind of show you a little bit of what's going on up here. Okay, you'll notice this area right here. See that thing? That's like a little stalk. Okay, you'll notice it's pointing right at this star. What's happening is this star, it's young, it's hot, and it's inside, it's embedded within a dark dust cloud. Okay, no longer dark because it's scattering. Its blue light is being scattered by the dust particles in here, and that blue light, of course, we look at, and this is the same, again, for the same reason we see blue sky. All right, so that's what's going on here. It's really cool. This stalk is the result of what's called erosion. Now, this star has very powerful stellar winds. You'll notice it's sort of made a cavity around itself. And that's what happens. Okay, when there's a hot young star in a dust cloud, it'll tend to push away with its stellar winds, push away the material around it, making a little isolated cavity around itself. That's what's happened here. But why didn't this go away? Why is that there? This is there for, among other reasons, potentially because the very end of it is pretty dense. This might be denser than that 30 atoms per sugar cube size. Maybe it's 30,000 atoms per sugar cube size, and that is enough to prevent the star's stellar wind from blowing it away. And so what it does is it protects what's behind it. All right? It protects what's behind it, and therefore this forms a stalk over time where this material that used to be around it was blown away, but this stuff here, the stuff at the beginning here, is resistant to the star pushing it away, and it protects what's behind it. So that's kind of how that works, you know. So it's kind of neat. Really, really neat. All right. Now, we also see in the Horsehead, we have very faint stars in the Horsehead. And as we move along here, we'll actually be able to see them better. Okay. But look at that. This is the Horsehead Nebula region. Now, this star that I kept just out of the view, right there, that's the halo from the star. You can see a faint halo around this. The halo is an artifact of our imaging system. However, if you look at this star that's just out of the shot, it's right about here in my view. You can't really see it, but it's right about there. That star is the leftmost star in Orion's belt, and it's called Alnitak. Okay, and it's really, really something. It's a beautiful image. I haven't seen this in a year. It was with the other telescope. Okay, so let's go here. Let's color correct again. Okay, that's good. It's color corrected. And now you can see more details. You can see now there's a star appearing on the back side of that horse's head right there. Hey, Derek Sperry, how's it going, man? Thanks for joining us. Make sure you like and subscribe. I mean, everything we do is free. You can pay if you want. We have a Patreon here. We have an Etsy store. You can buy images like this on sneakers and boxers, shorts, and cups and mugs. I mean, it goes on and on. And so we got lots of stuff, blankets and so forth. And Kathy Prentice said, hi, how are you? Nice to see you. And Kathy says, very striking. It is. It's beautiful. It's a very striking image. And this is, let me show you the full frame. That's the full frame of what we got here. You'll notice there's hydrogen gas over here, sticking out a little bit. And it's really a complicated region, but beautiful. I'm going to bring our telescope back for a minute. There we go. All right. And let's pop out of this. Okay. All right. Now let's bring back our stack information. Here we go. Docked up again. 12 images. It's good. I will save the horse head. But first, I am going to have it tell me that it's the horse head, or I'll just type it in. Okay, well, we got it. Okay, so we'll do this. We're going to say Horsehead Nebula target. And what we'll do now is get out of this. Actually, I'll save it with the annotation so you have it. Luis Rodriguez says, if you had the James Webb Telescope at your command, where would you point it first? I'll tell you where I'd point it first. TRAPPIST-1. I point it at the TRAPPIST-1 system. That's where I'd point it. Because that will tell us an awful lot about, potentially, whether there are planets with atmosphere. Now, I know the TRAPPIST-1's already been looked at by the James Webb. So that's kind of cool. Okay. Oh yeah, let's do this. Bring that right up to the top. That's the darkest view. But now if we zoom in here, you can actually see a little more detail in here. Look at this. Okay. This detail now is going in there. Got all kinds of detail in here. It's like you're looking down into a hole. And here is a beautiful stalk created by this bright star, in my opinion. We have another reflection nebula here. All right. So that's what those look like. We see these reflection nebulae like this. It's really cool. Yeah. Neato, neato, neato. That's right, Luis. That's exactly what I was talking about. TRAPPIST-1 probably has the most interest to me than others because 3 of the planets could be in the habitable zone of the star. But I will say this, okay? It is an M star. M stars are volatile, and so they could potentially strip away any potential atmosphere on a planet with solar flare activity, stellar flare activity. Wow, this is pretty. Okay, we're saving. All right, let me show you now what you get. Okay, so here I saved the, as you just see it, and so here's what you get. What you get is that image. If you go up to SkyTourLive.org, you can download this image you see right here, right now. It's probably already there. Okay, it's probably already up on our server. But you just got to go to SkyTourLive.org to see how to get to it and so forth. Yeah, Ranjit Nilakandan says, Orion is one amazing region to observe, and that's exactly true. It is. It's an amazing region. What's interesting, too, is this star here, Sigma Orionis. Now, stars are born as multiple stars sometimes. You have double stars, triple stars, quadruple stars. We're going to see a quadruplet in just a few minutes. But this particular star could have up to 6 components. Now, the way that works is several of the stars have very closely orbiting companions, and so when you add them up, well, it really much adds up, and you can actually see how you can have 6, and they could sort of be stable because you have 3 going around each other, and each of those may have a smaller companion, and boom, you've got 6 all of a sudden. Okay. We've got 18 images. We're gonna save this here. Wow, it's really beautiful. Lots more detail than we've ever seen. Okay, that said, we're going to pop out of it now. It's up in the server. It's not lost. We'll go back to our 1-second shot. I could never see the horse head with my amateur telescope when I was a kid. It was just too dim. Okay. I could see a little fuzziness around this, but that's about what I saw. Just like this. Okay. Okay, so here's what we're going to do now. I'm going to take you up north a little bit now. We will head down to the Orion Nebula in just a minute. But I want to show you this nebula right here. This is called the Flame Nebula. And the Flame Nebula is a fascinating location because the flame is right near Alnitak. All right, this is Alnitak right here, the leftmost star in the belt of Orion. All right, and we're gonna head east a little bit to bring it over to the right. As I do, you're gonna see something right here, this fuzzy thing right there, and that's called the Flame Nebula. Aurelio's with us. Hey, Aurelio. Aurelio's the coolest guy. He runs these programs at the Danbury Library in Danbury, Connecticut. I've lectured there many times, and he really does some cool stuff, man. Let me tell you. Hey, Aurelio, I have a question for you too. When I did the 3D printing class there, did I leave a box full of my prints there? A box full of my creator prints and so forth? Let me know, because I can't find it, and I got to find that. Okay, let's just do this now. I'm going to do another 25-second shot here. This here, yeah, you're the grooviest. This is Alnitak. It's very bright. It's an O-type star, one of the hottest stars in the universe. And so now we're going to actually do a image of it. Thanks, Aurelio, for letting me know. Okay, so we're going to our live stack now, and we'll see the horse head one more time before we lose it to the new image coming in. That's beautiful. Again, molecules in here, molecules of dust, carbon, silicon dust from supernovae and dying stars. Stephen Jarrett, how you doing? And there's the flame. Look at that. And you can see there's those two areas right there. Those two areas we just saw. Those two reflection nebulae. The horse head is down below here. Just below, right around here in our view. But we're focusing on the flame up here. And you'll notice it's really cool. And you'll notice there's a lot of dust up here because the stars are kind of cloudy looking. And that's, again, only because there's a lot of molecular clouds up here of dust that the stars are, shining their light through. And they make a scattering nebula that shows as blue like we talked about. Really cool. Let's color correct. First time. And that'll be, make it more brilliant. Look at that. So now let me show you how this works. you look at this and you say, oh, that line going through the middle. Let's zoom in a little bit too on that. That line of stuff going through the middle here is separating this nebula from this side. Actually, that's not true. That line of dark material is up here in the foreground if you look at my picture in the lower left, and the nebula is behind it, and that dark material is actually bisecting it, but from the side you wouldn't see it. The nebula would be here and that dark stuff would be here. And so you wouldn't actually get a true bisection like that. It would actually just be something sitting in front of the nebula, silhouetted by the nebula behind it. And that's what we're looking at right here. And if we go here, you'll see we see some red up here. That's hydrogen emission here and here. And the blue, that blue is reflection nebula. So we're looking at the colors of the universe that we normally see. We see blue reflection nebulae in here. We see hydrogen emission in here. And it's exceedingly detailed. This is really good. I'm going to actually enhance this right now. Okay, so watch now. Okay, now check out this area here. Look how much sharper that looks. I just sharpened it. I know it's hard to see, but I actually just sharpened that up and it looks something like, wow, crazy. I've never seen this much detail. Again, that's because our camera is tuned to this telescope for the first time. Beautiful. Look at that. Again, the Flame Nebula, and we will actually make the Flame Nebula. See, it's close enough where it already knows it. So it knows the flame. We're gonna make that the target. Okay, we'll set that as the target name. Yep. Beautiful. Okay, we'll save it with the annotations, so if you want to look at what's over here, you can do that. Okay, so now that's out there. So if you went out to our site, this is the image you'll get. You get that too, so you can actually look at all the different things that have been identified for you. Okay. Again, these rings around this, these are artifacts of our imaging system because it's such a fast system. Very fast system, actually. Yeah, man, it's something. Wow. Flame almost looks three-dimensional. That's like the first time. It's never looked this good. I'm just beside myself. See, here's the other me. And we've got 8 shots captured here and stacked. And if we could actually get a few more, I'm going to drop this down just a little, get rid of some of that noise a little more. Wow, I'm telling you. I'll pull this back just a little. Look at all this detail. Let's back out for a minute because I want to show you something. Alright, now I'm going to come over here and over-process it to show you what's hiding in the background here. Look at all this extra stuff. Look how bright that is. Look at that red nebula right there. Look at this extra stuff. Look at all this feathery stuff out here. All this stuff here. This is an incredibly messy area of the universe. And by the way, it's like the closest thing to us. This is about 1,500 light years from us. Right? The whole Orion complex is only about 1,500 light years from us. Incredible. We should do this again, what I was saying here. I'm going to take that, put it down, and I'm going to remove this, move it over, and now let's just do an imaging of this. So I'm still building the image in the background. It's stacked 11. Wow, that's something. Wow. Gorgeous. So this blue reflection nebula is here, and where the hydrogen is denser, the hydrogen will dominate. And so you'll see that even though there's blue reflection in here, you can actually see strips of blue peeking through. See that? Okay. Well, that's actually within the dust cloud that this hydrogen is also, because it's mixed in. but the hydrogen is dense enough so that the red dominates the scene. Okay? And so, where there's not as much hydrogen to get ionized, and there's more of the dust, well, then the dust will dominate the scene. Usually that's in close proximity to the stars. But in this particular case, you can see that it's already starting to form. There's a hydrogen ionized region around here, but the dust is taking over here. The dust is more dense here. Hey there, Susie Cat. Yeah, Ryan's. She's talking about the. Susie's talking about the how Orion looks in the sky. And when you're up in the northern latitudes, Orion will look like it's standing up in the sky. When you go to the mid latitudes, it's still standing up in the sky, okay? But like where I am, it looks like it's laying down, and then it stands up when you're looking directly south, and it's laying down again when it sets in the west, okay? And the same thing will be true, at different latitudes. The higher you go, though, the less it lays down, because it's, like at the North Pole, it would just go around the horizon, and you would just see it going around the horizon in the same exact orientation, pretty much, except for our 23.5 degree tilt of the axis interfering with that. Boy, this is something. I mean, this is really detailed. I'm going to see if I can add a little more detail in here. Timmy Lee to Spain, what's going on? Nice to have you with us, man. Thank you. Subscribe if you haven't, man. It's all free. Okay, I want to pull this up for just a sec. I'm going to bring this up. I'm going to see if I can enhance a little more here. I'm going to try and sharpen these little tiny tendrils. So watch as I do this. So keep watching the screen. You ready? Let's do it now. Okay. Let's go even higher. Okay, now look how sharp those are. Wow, that's impressive. That's really cool stuff. I've just never seen so much detail in the flame. This is the first time. Really immensely good image. Really happy with this. Okay. I'll drop my sharpening back down to 1.66. Oof, that's something. When you first move it, it gets a little blurry as it's doing a quick move, but then when you stop, watch, boom, it pops in sharper. Neat. Now, if you're looking at stars that are inside the dust, they're going to have a more red hue to them, and sometimes stars like this, they're deep in the dust, and so some of their blue light is also being stolen by the dust, like we talked about. And so you end up seeing these stars that look very much red, and that's because they may not be red, they might be white, but their light is reddened by the dust between us and them. That's why the sunset is red on the horizon, but not red when it's over your head, because more blue light is extracted from the sunlight when it's farther around the curve of the earth toward the horizon, looking through more atmosphere than when the sun is over your head. So that's why the sunsets are red. More of the blue light is taken out of the sunlight prism, which is red, orange, yellow, green, blue, indigo, and violet. And more of that blue is removed. So the sunlight is shifted kind of toward the red, because that's kind of what's left over. And that's something that's very common in the universe. We see that all over the place in the universe. with things that are actually embedded within dust clouds. All right, let's dock up again. Pull this up. Wow. Gotta say, that's beautiful. We got plenty of time. The moon doesn't rise until midnight out there. Alright, so we save exactly a scene. This is the image you get when you go out there, right here. Look at that. That's the image. Hang on, check it out. Okay. Let's bring the telescope back in, push that over. Alright. Okay, beautiful. Now we're gonna go check out another dusty region in the sky that I think you'll like. And we'll get to the Orion complex, don't worry. Alright, so here we go. Let's bring this down to that. Very good. Now let's go and head over to this guy. The longer we wait, the more the Orion Nebula comes up above the wall of our observatory, which is what we're waiting for. It's there now. We can probably do it, but it's going to be kind of more toward the east, and we prefer to have it more toward the south. But we're moving now to Casper the Friendly Ghost Nebula. You'll see a couple of stars. Okay. There they are. That's Casper right there. Now, let's go do this. Let's move this over. I have not imaged Casper with this camera. This camera, again, being tuned to the telescope. So this is going to be a real treat. Really looking forward to this. So you're going to wonder why I'm going down here right now. But there's a reason. Okay. And that is because I know how it looks. I know what it looks like. I know what's going on in the region. And I know that there's a lot of material right here that's dark that you want to see. That we all should want to see. So I'm going to move us back to here. Bonnie says that the Flame Nebula looked like a heart with arteries. It kind of did, didn't it? Okay, now there's more out here too that we're going to see. So, right, we're guiding now. See that? Our numbers come up. We start guiding. So this one I'm going to do for 30 seconds. We have dark stuff in there to take. And I'm going to increase the sensitivity to 250. All right. So this is going to be a little more noisy at first, but then it'll get better. But let's go back and check out the flame one more time. Oops, my mistake. I meant to take that off first, so it's going to empty the buffer. Sorry. But the picture's still up there. Alright. So check out the Casper the Friendly Ghost Nebula here in a moment. You'll say, wait a minute, that doesn't look too impressive. Not yet. Okay, we have to start getting the data. See where our black line is? We need it over here. So we're going to color correct first. And watch the red, green, and blue curves kind of line up under each other now. Ready? Here we go. Watch. Boom. Alright, you saw them move. Now the black, we want this to ride up that curve till it's almost to the top. And that's good right here. Alright, and then we're going to want to take this other side, the mid-range, which is the less bright areas. Now see what I was talking about? It looks like it's got hair falling off of it here. And that's what's going on here. It's not falling off, it's not hair. But what's happening is, okay, these two stars are not ionizing any hydrogen here because they're not either hot enough or there's not a lot of hydrogen in this region. But what's happening is there's a lot of dark dust, and the dust is dominating over the quantity of hydrogen. So we're getting this reflection nebula forming here, and you see the dust clouds here. And they go all the way down here and out of the view, all the way down to the bottom here. So I tried to place it in such a way that we can kind of end up seeing those. And then over here on this side, we're going to see a little bit more of the red diffuse stuff here and more of the material here. It's going to take a few minutes, but we'll see it. Unbelievable. Really looks nice. Yeah. Randall Smith says, "Are there such things as rogue stars with a rogue planet orbiting like when worlds collide?" Actually, that's a really good analogy. I mean, I guess in a sense every star is a rogue star, right? Although when I was getting my astronomy degree, my thesis was on runaway B stars. So I guess those are rogue stars. So technically, you're kind of right. I mean, we can have rogue stars. And I found a number of these hot blue B stars. Oh, look at this. Racing out of our galaxy at high speed. Now, why did that happen? Well, because in some of these O star and B star associations, they orbit quite closely sometimes, and maybe they got whipped out from a gravitational whipping force. You know, pass too close, they go whip, they whip out. And it's all in ultra slow motion. It's galactic slow motion, right? But that could be what's happened. And so that could explain why we had these rogue stars that formed in our galaxy, but now are freewheeling it out of the galaxy. Now, on top of that, you asked about rogue planets. Yes, in this region actually of Orion, it appears that there may be rogue planets here. Not where we are now, but down by the Orion Nebula. Yeah, looking at which we're going to end with in a little bit. That's where we're seeing rogue planet potential is down there. You notice a few areas of hydrogen emission that are happening here and just a little bit there. Okay, that's because we're seeing a combination of densities of material. The more dense the hydrogen is, the more red it'll appear, and the more it might dominate over the weaker reflection nebula. But look at the quality here. This is very dark and sort of lighter. I mean, this is really something. We're going to zoom in on this. We've only got 9 shots right now. Wow. Yeah, this stuff is my cathedral, let me tell you. You'll notice that you have a lot of stars here, and you almost see no stars back here. What's that? Well, that's because these stars in the background are there. They're being blocked by this dust in the foreground. You know, just like those other nebulae where you have the dark lines, this dark dust is passing in front of and circling around this bright blue nebula. If you can pass this dust cloud, this bright blue nebula is right there, including everything behind here. All right, so this is arcing out in front of it, and so you have the bright blue here, and this arcing thing coming over the top of it. So from the front, it looks like it's blocking it, but from the side, you can see it's sort of associated with it, but this beautiful nebula exists on its own, and the dust is kind of occluding it, mixing through it. But look at all this other stuff down here. Isn't that crazy? Let's see what else is hiding in here. Let's overprocess. Wow, look at that. All that stuff there. All this stuff here. And it's just an incredible region. This might be a region where a planet could form that could house life, because it's not in the middle of a stellar nursery that's so hot like the Orion Nebula. It's actually in an area that's a little bit cooler, and in the denser parts of this dust, you could actually be, as I said, if it's dense enough, like 1,000 atoms in a sugar cube space, that might be enough to protect the interior. And so the temperature in here might be minus 240 Celsius, minus 250 Celsius. Absolute zero is minus 273 Celsius. So you have something somewhat less than absolute zero, a little bit, I should say, higher than absolute zero, and it would be an area where dust forms icy shells on top of it. The icy shells will have formaldehyde, carbon monoxide, water, carbon dioxide ice, methane ice, methanol, and those would all be on these icy grains. And if a star forms in there, then those grains will be subject to heating, and that material, the ices, get driven off, and now you have literally a primordial particle bath of materials that can make planets and stars. And so that's pretty cool. Yeah, that's pretty. Wow, that is something else. I notice also, you see this dark material here, and for the first time I notice a subtle glow here. This was lost to us with the other camera, but here you can almost see like it's glowing from behind this object, isn't it? Look at that. That's pretty kind of cool. I can understand how that's happening. I can see it. All right. I'll just take care of one thing. Beautiful, man. Okay, so let's see if we can darken up the background enough to bring forward this stuff here. I'll do it by moving this forward. Oh, look at that. Yeah. And I'll pull this back just a little. See, by playing with the levels, we can actually gain a good perspective. Now you can see it. Look at the knots of dust in this area. Look at this. This is something. The dust it's all knotted up in here. You know, if you're running this on your screens, make sure you maximize it. And if you're casting it to your television, like a lot of people do, and sitting there with popcorn, enjoy the show, that's cool too. And but then you get the chance to see all the detail in here, and the detail doesn't show up unless we really zoom in on it, you know. So we zoom in on it, you can see this. There's that soft glow. Something's glowing bright behind this knot of darkness here, and it's silhouetting that. It's beautiful. You know, that soft glow is something I've never seen before. It was not available to us with the other camera. Cosmic Flow 888, what's going on, brother? Good to see you. Yeah, and now you can see this feather duster of dust. This is light years long. Light years. This is light years in length. You know, this is incredible. Okay, we got 20 here. Again, we're at 250 on our settings in terms of our sensitivity. Okay. Oops. Hello, come back. I had a little earthquake there. Okay. Okay. So these two stars are the ones that are powering this nebula. And if you look at it, you can see this lighter dust in here with little tiny tendrils on it. Isn't that something? And those little tiny tendrils are the beginnings of little stalks. And those little stalks are the result, most likely, of the stellar winds from these two stars in here. Bonnie Stanley asks, why doesn't it move? And what causes the dust? All good questions. Okay, the dust comes from supernovae explosions, and it comes from older red giant stars that are so big that they can make molecules in their outer atmosphere. And because many of the stars will have carbon in their outer atmosphere, we're going to get a lot of carbon-carbon molecules. Carbon makes a very nice bond with itself. Silicon atoms, silicon bonds can occur out there. And the dust is primarily carbon and silicon dust. But in the supernova, when a supernova occurs, and it could have occurred anywhere in the galaxy and then just swept through this part of the galaxy to provide materials with which you can build a star or another star or a planetary system, and then we would see this very thing happening. We'd see that we'd have lots of this dust. That dust will end up forming from those phenomena. A supernova or a planetary nebula, the death of a star kind of like our sun. Hey, Bill Connolly is with us, asking, bring me up to speed, what are we looking at? This is the Casper the Friendly Ghost Nebula. And it's in the constellation of Orion in the upper left right here of the belt. See the belt? It's right there. Okay. And so what I'm going to do is I'm going to bring up our guides. Okay, that's where our guides are. And eventually I'll show you what these guides do here. They allow us to calculate sizes of things, so we'll be doing that. Because we know how many light years per pixel exist or on our telescope. We just need to know the distance, and we can calculate it. So, knowing the distance to an object, you can figure out how many light years per pixel there are and figure out the size of objects and measure all kinds of things. It's really cool. Okay, we're going to go to 30 shots on this and then we'll stop. Wow, okay. More detail coming in now. I could have brought this down a little, but I wanted to capture what's down below here first. Okay, so that's what's down below here. So here's the full image of what we're looking at right there. Let's see if we pull this way in. And you can see all this brownish dust in here. This is all dust. Yep, that's something else. Really crazy. Oh, Michael, hey, thanks for coming in and saying that. Good to see you, though. You know, no harm done. No harm, no foul. You're always here. You deserve a night off. Wow. Okay. So let's zoom in on this again here. Alright, we have 30 frames, so we're going to save this. This will make a good finished shot. Okay, there we go. So what you get is you're going to get this shot right here. that carries all this stuff down here. Now, on another night, we're going to put this down here and capture what's above. But I won't do that tonight. Okay, so that's good. Gosh, that's beautiful. All right, we're going to move on to the next object now, guys. All right, and we're going to go back to our low light mode. And now we're going to do what I promised. We're going to head down and check out the Orion Nebula, this beautiful nebula. It's something. It's stunning, it's exciting, it's beautiful. Okay, so there we go. You'll see the nebula come in. Can't miss it. This is one of the few nebulas you can actually see with your eye. It's right below Orion's belt and Orion's sword. Okay, this is the Running Man Nebula. We're going to focus on Orion and Orion's Nebula and below. We'll do the Running Man another night. So I want you to see what's down below too, because there's so much down below. Again, the giant Orion Molecular Cloud Complex is down here. First of all, it's down here and beyond. Let's move west a little bit. This is all dark dust in here. You just don't know it. This is like a blister on top of the molecular cloud. Randall Smith asking about 3D imaging. The stars are too far apart to actually do that. However, the observatory we're in now is going to be 220 miles northwest of the Benson Observatory, provided we get the funds to put that in. And we'll be able to do 3D imaging of things like the moon, okay, which is going to be kind of cool. Even the planets will be too far away. But we'll be able to try doing this with the moon and seeing if we can actually generate a 3D image of the moon for the first time in human history. I think we can do it. Okay, so here is Demarane's Nebula, or Great Orion Nebula, Messier 42, and I'm going to do a before I actually do an exposure, I'm going to drop it down because I'm going to zoom in on the center here because I want to show you a quadruplet. Okay, here are 4 stars known as the trapezium, and I'm going to try something here just real quick. Okay, other way. Okay, so this particular let me just go down to say 250 milliseconds for this for a moment. So I want to show you the 4 stars really clear. All right, they're a little more, I guess. Okay, a little bit more. Okay, and that actually shows us that our focus needs to be done again, which is good. Yeah, it's really pretty there, isn't it, Donald? And then poof, you know, now we're seeing it like with more detail. Now here's what I'm gonna do. I am going to do a focus run here right now. I'll do it like this. I think we're good there. And we're going to focus now. Go negative side. It's using stars beyond what we're seeing on the screen. It's using all of the whole field. So if I back out, see, it's using a lot of stars. So I hope you guys enjoy what we do at SkyTour. I mean, again, we do it because we love it, not because we want to make any money at it, because we don't. We're not taking a dime. But we want to actually have 2 of the telescopes up and running at all times. So you would see in one building, you'd see the one telescope, and then the other view would be the other telescope, looking at what it's looking at. So that's kind of what we want to do. We already got our focus. Look at that. Okay. And we'll do a best focus now because we're already there. It might refine it a little more, but we're good. Okay. Okay. And now let's come back out. And let's go back in to this and see how well that did. The trapezium are 4 hot young stars. Actually, there's more than just 4 in there. But they're actually responsible for lighting up this entire area. Okay, so that's what we're seeing when we're looking at trapezium here. We're looking at these very hot young stars in there. See that? And there's 4 of them initially. All right. Okay. All right. So what we'll do now is we'll back out. Head back to our 1 second time, which is our low light mode. Okay. And then blast it. Okay, now let's do a I'll do 25 seconds. It'll really overpower the middle of the nebula, but it'll show you the dust around it, which is really nice. And we'll leave it at 250. Okay, so we'll come back to here and we'll do our live stack, and then I'll explain the colors. We'll get rid of that. Okay. Now check this out. Talk about mind-blowing. Look at that. Wow. I'll explain these in a minute. They were never there before, but they are now. There's 3 of them. There's one here. There's one here. There's one there. Now, we took a 25-second shot. What these are satellites. But not just any satellite. These are geostationary satellites. There's, you see, there's 1, 2, 3, 4 trails. So these satellites are over the same spot on the Earth. But we're following the stars. We're rotating out from under the satellites. So the satellites get dragged out as a line, and the nebula stays perfect because we're following the nebula, not the satellites. And there's more. But look at all this dust, huh? And it's going to get more and more and more. I'm telling you, it's crazy. Let's color correct. Okay, notice the color correction brings out the dust. Look at this little tendril of dust right here. Zoom. That is something else. And I'll pull the black level back just a little to help soften everything up a little so you can see it. Isn't that pretty? Now we have lots of dynamic range, so we can actually dig into the nebula by pulling that way down. We can go way more and then bring it back. Just incredible. The Orion Nebula, folks. And this again is dust from the molecular cloud, the Orion Molecular Cloud Complex. I always look at these two little stars here and I say, hey, those are kind of neat. Yep. So this is a very interesting location. You can see it's almost three-dimensional. And as we capture more images, I gotta change our full width f maximum a little bit. I want to take us up above. Take us up above that. There we go. See, and the satellites are rotating out from under us. Isn't that pretty? Alright, so let's talk about the nebula. Okay, this nebula is in a region, of course, it's just filled with many different elements made by supernovae and littered to the cosmos. The most prominent and copious element is hydrogen, and that is what we see as red here because the trapezium stars are so hot they're ionizing the hydrogen atoms, kicking the electron off the hydrogen atom, so it absorbs a lot of energy from the ultraviolet light, and then once it collides with other objects out there, it drops back down into the atom or a different atom, and as it cascades back down into the atom, it gives off light. The light it gives off is this characteristic red color. Over here, this stuff is, you'll notice it's kind of like teal. It's not that blue like we saw in the Horsehead region. This is ionized oxygen, but it's ionized more than once. 2 electrons are kicked off of the oxygen atom, and when it's kicked off, it absorbs a lot of energy, and when it comes back in, it gives off this characteristic teal colored light. And that is why we see these colors. The brown, that's just the natural color of the carbon and silicon slurry of material out here in the outer realm, the outer regions. Okay. But these stars, those 4 stars in the middle of the trapezium, are hot enough to ionize hydrogen way out here. This is about 20 light years across or so, 22 light years across. And the stars in here are ionizing it just fine. So they're very, very powerful. That's beautiful, huh? Let's have them name our target for us. Okay, and this will be Great Orion Nebula. And we're going to say target. Excellent. Okay. Now you might say, well, those satellite trails really ruin the shot. And you know what? They were never there. I've taken photographs of the Orion Nebula for years. Never saw these geostationary birds. Now we do. Now we do. There are some advanced algorithms, actually this software has it, to remove satellite trails, but it's a beta process and I don't want to have it removing too much data. I can get rid of the satellite trails in post-processing. Let's take a look up close here. Alright, if you look, you can see these sharp definitions of oxygen, right next to the hydrogen. Now they look sharp, but if you entered them, it'd be like entering a cloud in a jet. It's not sharp when you get up close. It's a gradual increase in density as you enter, and most likely you wouldn't even notice it. Actually, another thing is you can see the densities very clearly right here. Check this out. If we look at this spot in the nebula, here is an oxygen cloud right here. See it? That's oxygen. But we're seeing through the oxygen to this hydrogen spindle right here, this little hydrogen area. So this is not dense enough to overpower the hydrogen alpha behind it. Okay? But we're seeing through it. So it's sort of like a transparent, meaning it's a lower density than the hydrogen is. But the hydrogen's behind it. So this acts like a kind of like a gauze curtain looking in front of it. And we see a lot of that in some nebulae. But that's really fancy looking, I'm telling you. We could zoom in. Say, what if we lived like in here? What would we do? What would the Earth be like if it was inside here? The answer is the Earth wouldn't exist because it's too hot in here. It's too hot and the radiation's too intense. Besides, you wouldn't really even see the red. It would be very, very faint to you. You know, you'd see probably black space, and only if you took a photograph would you notice a glow, a dull red glow kind of all around you. And that's what we'd be looking at. Yep, that's how it works. Very nice, very nice. It's very nice. It's amazing to think that this stuff actually exists out there, huh? Isn't that crazy? Look at that. Look at that. Wow. So let's try bringing it in a little bit, get some detail. Notice that as we get up to 16 shots, this material looks more and more smooth. It doesn't have the same graininess that it did when it originally was taken. Crazy stuff. Beautiful. On another night, we'll do the Orion Running Man Nebula, rather, up above it for a similar amount of time and set up, and then we'll actually stitch them together. I'll probably show those to you as well. Kind of fun though, huh? JSCO wants me to talk about M43, which is this little piece up here. This is just an extension of the nebula, identified as separate from Measure 42. And particularly this dark nebula seems to sit in front of it. But in reality, this nebula here and this nebula here are probably all part of the same structure. The oxygen is very dense in here. And so the oxygen being this dense probably prevents us from seeing the relationship between the connection of this hydrogen and that hydrogen. One thing to keep in mind, I mentioned hydrogen is the most common element in the universe. But you have to understand too that the next most common element is helium, because hydrogen fuses into helium. But then the next most common element after helium, you ready, is oxygen. Oxygen is the third most abundant element in the entire universe. You know what the fourth one is? We know helium is second, we know hydrogen's first, and we know oxygen is third. The fourth most abundant element in the entire universe is carbon, that from which you are made. So what it means is that we are looking at a universe that seems to be predisposed to making carbon-based life, doesn't it? So I've become kind of like what they'd call a carbon bigot. Okay. I am. I think that carbon is probably the basis of most life in the universe. Now people say, well, silicon-based life, how about that? I've seen Star Trek with the Horta, no kill I, right? Cry for the children in the halls of tomorrow. You know, well, silicon-based life is a tough one. I'll tell you why. You look in the periodic table, you have carbon, okay? And then just below carbon is silicon in the column. Well, those atoms in those columns are those that are most like each other with characteristics and capabilities. When you go from carbon to silicon, the silicon atom is far different in its ability to bond with things than the carbon atom is. The carbon atom is actually known as the granddaddy of elements because it can bond with more stuff, with more other elements, create, make, and break bonds more easily than any other element in the periodic table. As we sit here watching me talk about the Orion Nebula and carbon, your body is made and broken thousands of bonds as we sit here, and it's all carbon bonds. So that process that's happening is something that makes carbon rather unique. It's easy to bond, it's easy to break. And that's something that life requires, this flexibility. Silicon now, let's go to silicon. Silicon tends to make crystal lattices, crystalline structures, crystalline bonds, because of the nature of how it works. And when we talk about silicon, it doesn't have the ability to make and break bonds with nearly remotely the ease that carbon can do it. So carbon atoms seem to be the most naturally selected atom for life to me. It's the basis of my book, The Populated Universe, is carbon-based life. So it makes sense. Now, silicon, when it makes a bond, it doesn't want to let go. And so when we talk about silicon bonds, one prominent example is the beach. Go to the beach. And the sand is silicon dioxide. One silicon atom and two oxygen atoms. Silicon di, meaning two oxide, two atoms of oxygen. Silicon dioxide is very hard to break apart. And when we go to the beach and when you're walking on the beach, you can use this if you want. You can say to your friends, do you know we're walking on mostly gas? And they go, what are you talking about? What have you been drinking? No, it's true. We're walking on a silicon atom and two oxygen atoms in sand. You're walking on mostly gas. And people go, oh, my brain hurts. Because it will. Their brain will hurt. But yeah, you can use that, guys, free of charge. No charge. Okay, so silicon dioxide. Amazing stuff. I'm going to color correct here. Hey, look at that. That last color correction now really brings out this dust. Look at that. That's not light leak. That's not like light. No. That is the brown dust. The silicon dust that we're talking about. And the carbon dust. Gorgeous. Now we'll save this. I'm going to actually save this one more to come in with it. Save it at 30. There we go. So we'll save it at 30. And then we'll save exactly as seen. Ba-boom. So the image you'll get when you go up to skytourlive.org is this image. You're free to take it. You're free to use it, do what you like. Explore it. Hang out with it. Tell it you love it. Whatever. And you can actually see the beauty of the universe this way. I hope you enjoyed that. So tonight was a kind of a banner night. We went through the winter sky together. And we saw some other things really cool. There's so much more to see. But I'm going to end up heading to bed now because I have to be up tomorrow early and drive several hours away. But that's not a big deal. So you guys, I hope you had a good time tonight. I hope you enjoyed this. And I hope you enjoyed all the things we looked at tonight. All right? And the commentary from your friendly neighborhood Spider-Man. No, friendly neighborhood astronomer. Anyway, you guys have a good night. And we'll see you on the next clear night. Good night, everybody.
Stars so bright in the sky, on Arizona nights they fly. Nebulae in colors rare, galaxies beyond compare. Sky tour in the night so clear, brings the universe near. Real-time wonders to see, streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views, every night feels brand new. In the dark, the night unfolds, stories of the cosmos told. Through the lens, a distant dream, living real like a gleam. Far away, up so high, across the stars beyond the skull. Through the lens, a distant dream, living real like a gleam. Lift your eye up so high, across the stars beyond the sky. Sky tour shows us the way, every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views, every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views, every